So hi everyone, my name is Suan. I'm a data scientist at Clarivate. Today I'm going to be talking about a model that we've been working on for about a year or so now. And I'm going to be starting with the business problem and why a machine learning model was the right solution, the actual modeling and the performance of the model, and also the business impact of the model. So this talk is called Stacked CNNs in Hierarchical Classification of Medical Text because they're convolutional neural networks. So our clients are 8 medical device distributors. So they basically distribute medical devices to hospitals and other facilities like that. And each of them wants to know what their market share is in different market segments. So to do this, we need to solve for the following equation for each market segment. So say if surgical gloves is one market segment, we need to know the number of surgical gloves distributed by distributor A, and we divide that number by the number of surgical gloves distributed by all distributors, right? Then we can say, this is the market share distributor A has in surgical gloves. So it's actually a lot more complicated than that, right? Because first of all, each distributor organizes their inventory differently. For example, pH test strips and pH indicators can be considered one category for distributor A, and it can be considered 2 separate categories for distributor B. And secondly, we have a lot of medical devices and equipment to sift through. At the time when this problem came to us, there was like 3 million rows of products that we have to look through in our backlog, and we get new batches of data every month. So that's obviously a lot of data for a human to do. And lastly, simple rules cannot be applied because of the quantity of data, and also data is very dirty, full of abbreviations, typos, just like very dirty medical text kind of things. So to solve the first problem, which is that each distributor organizes their inventory differently, we have to bring in a universal taxonomy system for everybody to adopt. So we decided to use the Unspec system. So Unspec stands for United Nations Standard Products and Services Code, and is a taxonomy system that classifies all commercial products under the sun. It has about 4,000 categories for medical devices that we see in our data. So by adopting the Unspec taxonomy, we will be able to solve for the market share each distributor has in each Unspec category. So now we're using one Unspec category as our definition of like a market segment. So, and the next 2 problems are that it would take too long and cost too much for humans to do the classification work. It's very difficult for a human who is an expert, right, to look at one line of very obscure text and decide which of the 4,000 categories it's supposed to fit into. And also that the texts are very dirty and it's not feasible to use simple rules. So these 2 things combined makes this like a particularly suitable problem for a machine learning model. And so we decided that what we needed is a machine learning model, and we want a model that can take in information about the product and output the right Unspec classification for that product. So I'm going to go through how we make that model and what it looks like. Okay, so this is the framing of the model, which is very, very simple. The input is really just the text that describes the product. So you can see here it says stalking, anti-embolism knee, regular XXL, 10 per carton or maybe 10 count, who really knows, and Carlin wound care, skincare, etc., etc. And we give this to the model, which is what we have to make. And we want the model to say, this is category 421422802, which points towards the Unspec category for vascular or compression apparel or support, right? So to reduce it to a more feasible problem for the model, we only use the Unspec categories that we saw in the label data. So we narrowed our scope down to about 4,000 categories. And then we reframe the problem as a binary problem. So typically in a classification model, so this is how our data looks like. In very simple terms, you have product text. So the first line, it says pheno, probably meaning phenobarbital. And then you have the second column, which says distributor taxonomy text. Here, you know which distributor it belongs to. So distributor A, and distributor A classifies this product under distributor A's own categories, which are medical and pharmaceutical drug, let's say, right? And let's say we know that this belongs to Unspec category 51132222. So we say that that's a 1, meaning it belongs to this category. Then for the next category, we say 0 because it doesn't belong to that. So this is basically a one-hot encoding. And for 4,000 more categories, it's just 0000, it doesn't belong there. And we do that again and again for every single row of data. So if we do it this way, then every single time the model looks at a product, the model has to pick one right answer out of 4,000 categories, right? So that's like high cardinality, and it's kind of hard to pick 1 out of 1,000. So we reframe the model, we reframe the problem into a binary problem. So if you look at the second table, instead of doing it the first way, we now say the product text is this, we concatenate it with the distributor taxonomy text, and then we concatenate it with the unspec text that describes the unspec category that we know is correct, right? So in this case, there'll be 51132222's unspec text. And we tell the model that this has a label of 1. And then we do the same thing again, but this time we pair it with an incorrect unspec text, and we tell the model this is 0. So basically, now the model is not asked which of the 4,000 categories. The model is asked, does this product match this category? And the model says yes, no, right? So in testing, each product is matched with every possible unspec category text, and the model predicts a value between 0 and 1 for each match. And the one that is closest to 1 is picked as the predicted category for that product. To make things clearer, so this is an example of how unspec looks like. If you look at the first table, the first column is the ID for the category, and the second column is the title of that category, and the third column is the descriptive text. It sort of tells you how to classify using that category. And the second table is really like how our data looks like when it comes into our system. So for example, if we wanted to ask the model for the first row of product, does it belong to the first category we see in this table, we would construct our feature text in the following way. We will concatenate the item description, and then we will concatenate the category in the second table, and then the subcategory 1, subcategory 2, and then we would match it up with the unspec text of the unspec category we're interested in. So that will be the first row, and it will be fibronopeptide A immunological test system, blah, 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 blah. And you can see that in the orange text. And you give this to the model, and the model will say 1 or 0, right? Match or no match. So the unspec taxonomy system is a hierarchical tree system. And there are 4 levels in total, with level 1 being the least granular and level 4 being the most granular. So we have an option to actually make 1 model per level, or at least more than 1 model, right? To make it an easier problem for the model, because then the model only has to look at fewer choices and pick the right one, instead of having to look at 4,000 and pick the right one. So what we ended up doing is we have 1 model at level 2. So at level 2, there are only 200 possible categories. The model only has to pick the 1 correct answer out of 200. And once the model picks that answer, we pass that answer down to the level 4 model. And we only show the level 4 model the choices that are still available given the level 2's prediction, right? And we don't show the model all the choices that have been ruled out. And now the level 4 model only has to make the right choice out of, worst case scenario, about 300 to 400 categories. So that's significantly less than 4,000 categories. So at the end, after some trial and error, this is the architecture we ended up with. So you can see the input is still the same, right? but instead now it's going first to the level 2 model, and the level 2 model gets the product descriptive text, and it now constructs the feature text using the unspec text for all the possible level 2 categories. And the level 2 model picks 42140000 as the best choice. So the level 4 model gets the product information, and it also gets the level 2 model's decision. And now it only looks at the unspec descriptive text of level 4 categories that fall under 42140000. And in this particular case, that's only 280 choices. And out of the 280 choices, the model picks 42142802. So that's the right answer in this case. Yeah, so as for the models themselves, they both have a similar structure. They both have exactly this structure. And they're both neural networks. So there's an input layer, and we go into an embedding layer, which I'll come back to. And then it goes through a CNN, a batch norm, another CNN, another batch norm, flatten, dense, drop out, and then output. So it's not super complicated. We tested this out, worked really well. Yeah. As for the embedding, we use BioBERT for level 2, and we use a word2vec that we train ourselves for level 4. So BioBERT is, they used the BERT model, and they pre-trained it on PubMed datasets so that BioBERT really understands medical text, and it understands medical terminology like antibiotics or insulin or things like that. It's able to handle tasks relating to medical text better than BERT, the original BERT. So we tested it out, and it worked really well for level 2, because at level 2, it's still high enough level that you see a lot of these words in like complete form, and the model picking out these meanings was very valuable, and it was able to classify these things really well. We tried it out as well for our level 4 model, and the model absolutely was not able to learn at all. And I think the reason is because at level 4, the text just becomes so dirty that you have to, the model has to understand like medical codes and numerical codes that actually point to drugs and things like that. And BioBERT just wasn't trained to that level, maybe. So we train our own word2vec, and it works very well for level 4. Yeah, and the sizes of the layers are different for both models, which we determine by doing hyperparameter tuning. Okay, so now I'm going to talk about the results, how we evaluate that. So we first get our training data, and we split it into training, validation, and test set. So validation set is used during training to check for overfitting, and test set is used to evaluate the model performance after training. And the evaluation is used to inform us on model performance in deployment. And it's basically our best approximation of how the model will behave in deployment, right? So what we do is we measure the accuracy of the model at each confidence score for the test set. And in deployment, the model is allowed to make autonomous predictions above K, where the model's accuracy is 90% or greater above K. So we don't hold the model to like unrealistic standards. We don't say that a model has to be 100% correct, because the alternative system to using the model is actually having subject matter experts looking at these things row by row. And humans are imperfect as well. Like we estimate that humans are likely to be at 90%. So we say the model has to be at 90% as well, right? And K is determined by our subject matter experts, who we work very closely with. So on the business side of things, the first model we deployed had 34% coverage. So what that means is the model was able to make autonomous predictions on 34% of the data coming in. And the second model we deployed, the coverage increased up to around 40%. And the third model is currently being evaluated. So we only push a new model out to deployment if it has an increased amount of coverage, right? So it's now a better model than the previous model. So this has helped us label hundreds of thousands of rows of data autonomously, and also sped up manual subject matter expert labeling for roles where the model is not able to make autonomous predictions. Right, deployment. So the model is now deployed. We use Spring Boot to deploy the model. If anyone is interested in how you get a model trained in Python, TensorFlow, to be in Java behind an API, I can talk all about that later. But basically, the way you use the API is you ping our URL and you tell the model, this is the product description, and this is the taxonomy, this is the distributor, and I want top N means you tell the model that you want the top one prediction, right? So you can set this to 5 in cases where, you're not asking the model to make autonomous predictions, but you're using it as like an aid for labeling. Then you can ask the model to give you top 5 predictions, and you can have a human pick, which one's correct. Anyway, so you ask for top 1, and the model responds and says, says 201, etc. This is the model version right now, and this is the Unspec ID. This is the confidence score, and it has a rank of 1, meaning this is the model's best predictions.
What are the sources of data?
So that's a really good question. So, well, the data comes from our clients, right? So our clients are medical distributors, and they have all these data, and they basically want it classified. So I guess maybe the question is, where is our label data coming from? So labeled data is very difficult to come by, and we work very closely with subject matter experts who help us iterate on the labeled data. So some of these data came in with unspec codes already, so they were already labeled, but they weren't like very clean or anything like that. And when we started working with it, we started to see that they weren't clean. So there were many iterations with a team of labelers, a team of expert labelers. We would train a model and we would send the results to them, and they would be able to pick out inconsistencies in the training data. They will work very hard to clean it. They will send it back to us. We will train another model, and we will find more inconsistencies in the data. We send it back, and we iterate until the data is clean enough to give us like a high quality model. So working with this team of labelers was a huge part of getting the model working. It was a huge part of the process. Almost bigger than the modeling itself. So yeah.
What's your loss function and how do you choose it?
That's a good question. I actually have to check my loss function right now. So maybe I know what the question is pointing at. Is that does the model know that these classes are exclusive of each other, which means, if this row of data belongs to category 1, it's not supposed to belong to category 2. And the answer is that no, the model doesn't know that. And the reason it doesn't know that is because it was really hard to set up the problem in a way that we can communicate that information to the model, because each row of data went in independently, and the model just says yes, no, yes, no. Let me just check the loss function right now. You can give me a minute. Sorry, 1 second. I'm just looking at my code. I wrote this like last year.
No worries. Take your time.
Sorry, I can't find it. Can I come back to that? I'll
Yeah, that's
message
okay.
you.
You mentioned that BioBERT works better than BERT for medical data. Is it for this specific labeling task, or do you benchmark it with other tasks too?
So BioBERT is better than BERT for medical tasks is something that the people who wrote the paper about BioBERT said. We never tried traditional the original BERT for this model. BioBERT was the first thing we tried, and it worked very well for us. So we never really switched that around. In like a lot of sorry, let me just the loss function is binary cross entropy. So I'm just going to type that out right now. Yeah, I imagine that it would be better because of the training data that they use to train BioBERT, right? Because it's PubMed. Whereas BERT is trained on Wikipedia and English books and things like that, and the internet in general.